Hey students, today we are going to be covering chapter number 1, chemistry, atoms, molecules, and chemical arithmetic, topic 1.2, particulate nature of matter. Before we start, we need to understand what does particulate nature mean. What do you know about particulate nature? Basically, particulate nature means when a big substance is made up of a large substance is made up of very tiny particles. It can be small substance also, but suppose you have a substance, it can be any substance. Suppose we have here a TV, okay, and TV is made up of, if you look closely, if you zoom into the TV, if you go closely to the TV, you will find that the TV is made up of very tiny pixel, something like this. You will know that the whole TV is made up of these very tiny pixels. I cannot draw the whole thing, but get the idea. Imagine it, right? Even your phone, even your tablet, even everything around you. Okay, so many people believed. Okay, many people believe that atom was made up of very small tiny particles, and thus it has particulate nature or it has particle nature. Okay, here matter is composed of large of number of very tiny particles, thus has particle nature. Not atom, sorry, but matter. Now, people before, Greek philosopher Plato and Aristotle, and many people, okay, including Greek philosopher and Aristotle and Plato, they believed that matter is continuous and the process of subdivision of matter can go on. What do you mean by subdivision? So imagine I have here the same TV. If I cut this TV, or imagine, I'll take a different example. Imagine I have a rock, okay, or I have a circle. If I take this circle or a rock which is shaped as a circle, okay, and I cut this, I can divide. So now I divide it into 4. Now I divide it again. Now I divide it into more. Then again I'll divide, again I'll divide, again I'll divide, and again I'll divide until it becomes tiny, and I'll keep dividing these tiny particles. I'll keep dividing it, okay? I'll take one piece of this and I'll keep dividing it. So many people, including Greek philosopher and Aristotle, believe that you can divide these matter, anything in the world, into small substance, and it can keep going on till infinity. You can keep dividing it, okay? But on the other hand, people believe that matter is made up of tiny particles, thus this process of subdivision is only limited. They believe that it is limited amount of times. You can do this only a limited amount of times, and thus it has particle nature also. Okay, now the people, Greek philosopher Leucippus and his student Democritus, they were the first to propose the idea. They gave the tiniest particle, like when you divide matter, so they saw the tiniest particle. The group of people that believe that matter subdivision is limited, they found the tiniest particle and they named it atom. And this idea was proposed first by Leucippus and his student Democritus in 1440 BC. However, before them, there was this person, Maharishi Khanat. He had proposed this idea of atom. He has proposed the idea of atom way before them in 500 BC. Way before them in 500 BC. Okay, 60 years before them. And what did he name it? He named atom as Parmanu. He named atom as Parmanu. So the other name of atom is Parmanu. Okay, so this concludes the particulate nature of matter's topic. And today we're going to be continuing into law of chemical combination as well. Okay, so we're going to be discussing about law of chemical combination. Now, in law of chemical combination, what do you mean by chemical combination? Chemical combination is basically chemical reaction, mixing chemical here and there. There are total 3 laws of chemical combinations that we are going to be discussing today. How many laws? 3 laws. There are going to be 3 laws of chemical combination that we're going to be discussing today. The first one is law of conservation of mass. Law of conservation of mass. The second one is law of definite proportion. Law of definite proportion. And finally, we are going to be discussing law of multiple proportion. Law of multiple proportion. Let us start with law of definite proportion. What does law of definite proportion mean? Okay, law of definite proportion, its statement states that in every chemical reaction, total mass of all the reactant is equal to the mass of all the product. Again, I will repeat again. In a chemical reaction, okay, in every chemical reaction, total mass of all the reactants is equal to the total mass of all the products. What does this mean? This means that when we have a chemical reaction, okay, when we have a chemical reaction, the total mass, what is mass? Mass means the mass of the product, the weight of the product, mass of the product, and the mass of the reactant. Okay, mass of the product and the mass of the reactant are equal. This is the whole law. The law states that the mass of the product and the mass of the reactant is equal. So if I have 2 reactants, so these 2 reactant combined, if they give one product, so these 2 reactant combined, their weight is equal to the product. Okay, it basically says that mass can neither be created nor destroyed in a chemical reaction. So you cannot have more weight after a reaction. You cannot have a reactant that weighs more. Okay, they will have equal weight, and this was proved by Anthony Lavoisier. Okay, a French chemist, Anthony Lavoisier. What did he do? Okay, Anthony Lavoisier used to study balance to study chemical reaction. Okay, so he took one day, he took mercury. Okay, he heated mercury in a sealed flask. So he took mercury and there's a sealed flask. Okay, he took mercury and he put mercury inside the sealed flask. This sealed flask had air in it. Okay, and he closed the flask and he heated it. Okay, after several days he came back and he saw that there was a red substance inside. Okay, he found out that inside the flask there is this red substance, and this red substance was identified as mercury dioxide. This was identified as mercury dioxide. Okay, when he found out this was mercury dioxide, he also found out that the gas remaining in the flask, when he put the experiment, the flask had gas trapped in it. Now when he looked at the gas, he checked the gas, it was reduced in mass, means it was less in weight. Okay, and the gas which was remaining in the flask had it did not support combustion. It did not support combustion, and it did not support life. And this gas was found out to be nitrogen. Okay, I'll go over it again. So this French chemist Anthony Lavoisier, he took a sealed flask. Inside that sealed flask, he put mercury. Okay, mercury which is not red in color. Okay, so he put mercury inside the sealed flask. Then he heated the sealed flask. Okay, sealed flask means it has air. What is air? Oxygen, nitrogen, etc. in it. Then afterwards, after a couple of days, he opened the flask again. Then he saw in it was mercury dioxide, which was a red color substance. Okay, and he checked the weight of the gas. The gas was less in weight. Okay, and there was this remaining gas which did not support combustion and it did not support life, and this remaining gas was identified as nitrogen. And then he found out that the gas that combined with this mercury was oxygen, thus it was mercury dioxide. So the gas which was in the air was nitrogen and oxygen, and the oxygen joined with the mercury, making it red in color and forming mercury dioxide. Okay, so that is what Antoine Lavoisier did. Then he took this mercury dioxide. The experiment is not over yet. He has to prove the law of chemical. He has to prove law of conservation of mass. This is not the proof of law of conservation of mass. He's proving it. Hold on. Okay. Then after that, he weighed the quantity of mercury dioxide, the red substance that he found in the sealed flask. He took its weight, and then after that he put it again into a flask and he started heating it. Okay, he heated it, and the red color, the mercury dioxide, he heated it. Okay, then it decomposed, means it was mercury dioxide, it split. Okay, it split into mercury and it split into oxygen. Okay, and then he weighed the mass of mercury and oxygen, and he found out that mercury dioxide, okay, mass, example, it is 12 gram. It was equal to, this is an example, okay, it was equal to mercury. Suppose mercury's mass was let's say 6 grams. Let's say 4 grams. Okay, and then he found out the oxygen's weight was 4 plus how much is 12? 4 plus 8, right? And he found that the oxygen weight was 12. This is just an example. So he found that the mass of mercury dioxide along with the mass of the product was equal, hence proving the law of conservation of mass. The mass of the reactant is equal to the total mass. The total mass of the reactant is equal to the total mass of the product. That is law of conservation of mass. So we are done with law of conservation of mass. We can move on to our next. Law of conservation mass is done. Now we have law of definite proportion. Now, the statement of law of definite proportion states that in a given chemical compound, the proportion by mass of the element that compose it are fixed, independent of the origin of the compound or the mode of preparation. This statement, we will come to it. I will explain the statement, but this was proved by French chemist Claude Berthotel and Joseph Proust, who worked on ratio or mass of two elements which combine to form a compound. This was done in 1808. So what happened is that in the law basically states that in a chemical compound, the proportion by mass of the element that compose it are fixed. For example, if you take water, okay, example, you take water of your well, if you have a well, okay, and if you have water from the restaurant, okay, and if you have water from the river, if you have water from the ocean, if you have water from your fridge, if you have water from the tap, all of this, what is their chemical formula? H2O, right? Water's chemical formula is H2O. Everywhere you go, you will find H2O only. If you see in ocean, if you see in the fridge, if you see in your tap, everywhere water is H2O. It is composed of 2 hydrogen and 1 oxygen. Basically, the law states that that the ratio between the compounds, so the ratio of elements in a fixed compound, so the ratio of hydrogen and oxygen in water is same regardless of the origin. So anywhere you take water, it has the same ratio, which is 2:1, 2 hydrogen to one oxygen. So wherever you go in the world, you take water from anywhere, water will be made up of the same amount of hydrogen and the same amount of oxygen. This applies to all the fixed compounds. For example, CO2 everywhere you go in the world, it will be 1:2 ratio, one being oxygen and one being carbon and two being oxygen. So 1:2. Wherever you find carbon dioxide in the world, its ratio will be 1:2, 1 carbon and 2 oxygen. So basically the ratio of an element is fixed regardless of its origin, okay, independent of its origin or mode of preparation. It is always the same, okay. That is basically what Joseph Proust and Claude Berthoudel proved in 1808. Now comes the law of multiple proportion. Here there's one point that you need to know, that reproducible results indirectly hint for a truth which is hidden, okay. You just need to know this point. There's nothing much to explain, okay. Now we can jump into Dalton's atomic theory. Dalton's atomic theory we learn a lot more in the next heading, which we're not going to be covering today, but we're just going to be learning one of Dalton's atomic theory, okay, which was the law of multiple proportion. He explained in his theory, Dalton's atomic theory, he explained conservation of mass as well as law of constant proportion, okay. And he also brought a new law, which was the law of multiple proportion, also the law we are going to understand. So what does law of multiple proportion say? When two elements form more than one compound, the mass of one element in these compounds for a mixed mass of the other element are in the ratio of small whole numbers, okay. So basically it's same as a law of conservation of it's same as the law of multiple proportion, law of definite proportion. It is same as that. It's just a little more detailed than law of definite proportion. Basically in a chemical reaction, example I have H2O, or if I take example of carbon and oxygen, okay, if I take carbon and oxygen, so in carbon and oxygen, I can make a different sort of compounds. For example, I can make CO, carbon oxide, or I can make CO2, carbon dioxide. I can make so many more such compounds, right? But the ratio of one compound is fixed, okay. So if I want to make carbon oxide, it is 1 carbon and 2 oxygen, right? If I want to make carbon dioxide, it is carbon oxide is 1 carbon and 1 oxygen, and carbon dioxide is 1 carbon and 2 oxygen. So no matter how much I add, one element is always fixed. See, carbon is always fixed here, right? For two elements to form more than one compound, which is oxygen and carbon, they form more than one compound. They form carbon oxide and carbon dioxide. They form many more other compounds as well. If I take hydrogen and oxygen, we can make H2O, we can make HO, we can make many more carbons, right? These, we can make many more carbons, so many more elements, right? So these element here, see, hydrogen is in 2 and oxygen is 1. Hydrogen is 1 here, oxygen is 1. So which is fixed here? Oxygen is fixed, right? Oxygen is fixed, it's not changing. So for two element which make more than one compound, the mass of at least one element is fixed, in ratio of small whole number. That is all that chemical law of multiple proportion is stating. And that is it for today's class. Thank you so much for watching. Goodbye.